Cations that can be acidic or basic. Actually, not really. It depends on what we're talking about. For Bronsted, let's look at Bronsted acids and bases. Cations, normally we don't think of it, like sodium, potassium, etc. In other words, the group 1, and then calcium, strontium, barium. The book says the cations of the strong bases, the hydroxides, are neutral. So these are neutral. What they have in common is they're all the cations for the strong bases, the soluble hydroxides. But the other cations are typically acidic. So this is something I didn't talk about earlier, but something like hexaqualuminum. This is acidic. And this is like comparable to something like acetic acid in terms of acidity, 0.1 molar. But what makes it so acidic is the metal ligand bond here. The metal is a 3+ cation. And what that's going to do is it's going to suck electron density away from the water, or the aqua ligand, via the inductive effect. And so it's going to make these hydrogens much more positive than they normally are in water. I mean, if we compare it to neutral water, there isn't anything sucking the electron density away from water here. And so the amount of positive charge that's built up on the hydrogens is considerably less here. And so it makes these much more acidic than in normal water. So if a base comes along, the base is going to be more attracted to a proton in the complex than a proton in water, like a base like hydroxide. And so this proton will be attacked before this proton. All right, so these other examples would be, there's other, the iron. And so even though these don't seem like Bronsted acids, they are Bronsted acids. All right, then we have things like ammonium and the amines. They aren't really called amines, they're called the onium ions. So rather than, if we had replaced some of these with a carbon, like trimethylamine would be called trimethylammonium ion. And so these would be the derivatives based off the amines here. And these would all be acidic. For the anions, it's a bit easier. We aren't going to be dealing with too many of these, calculating the pH. The aluminum, yeah, the iron, yeah, but not so commonly. The anions are, just look at the chart. Pretty much the chart is going to list all the anions you're going to encounter, or most of the anions you're going to encounter.
Which chart are you talking about?
The acid-base chart, the acid-base chart, except, the chart, when you consult the chart, you have to read the little footnotes. So for example, here, the chart would list chloride as the base. And so we have HCl as the acid and chloride as the base. This is a conjugate pair. And so when we look at the chart, should bring it up, but the chloride, you have bromide, iodide, nitrate, HSO4 minus. The conjugate base, that is the anion, that's a conjugate base of a strong acid, or neutral. And so these are considered neutral, quotation marks. These are too weak of bases to hydrolyze water. And so what that means is they don't impact the pH. So chloride plus water would yield what? HCl plus hydroxide. Let's figure out what the Kb for this is. The Kb for chloride is equal to Kw divided by the Ka for what acid? What's the conjugate acid of chloride? Hydrochloric. Ka for hydrochloric you should have in your memory. What is it? Very large. So if we're dividing by a very large number, this number comes out to become very small. And so if Kb is very small, then it's pretty negligible, the amount of hydrolysis. And so this is what we call the conjugate base of the strong acids. This is all written on that chart. The exception here is that HSO4 minus, all these have a very small Kb. The HSO4 minus has a big Ka. The Ka value for HSO4 minus is 0.011, which is significant. So in terms of base strength, it's nothing. In terms of acid strength, it's significant. These ones don't have any Ka associated with them. These are just, and we have others. What are the 7 strong acids that you memorized? What am I missing? So I got 1, 2, 3, 4, 5. I'm missing what? I have sulfuric acid forms hydrogen sulfate as its conjugate base. Perchloric acid, which would be ClO4. That's actually up at the top, but I ran out of room. ClO4 minus. And what else? Well, it's a chlorine, it's chloric acid, but chloric acid, some people, chloric is fairly strong though. All right, so the anions, the other anions are going to be quite basic. So for example, carbonate, carbonate's a dibasic base. So if we look at carbonate, we have a Kb1 for this and a Kb2. And so if we look at carbonate, carbonate's strong enough to hydrolyze water, significantly. And so carbonate and water will form bicarbonate and hydroxide. And Kb1 for this is equal, or actually Kb1 for carbonate, I'm almost done. Kb1 for carbonate is equal to Kb for carbonate, which is equal to Kw over Ka for what acid? Bicarbonate. And so we look up the Ka value for bicarbonate, and this is significant. This is fairly basic, actually. This would be the Kb1 step. Kb2 is that the bicarbonate is also a base. Bicarbonate plus H2O liquid yields carbonic acid, H2CO3. H2CO3 will decompose into H2O liquid plus CO2 gas and hydroxide. And so this is Kb2 for carbonate, which is equal to Kb for bicarbonate, which is equal to Kw divided by Ka for carbonic acid. But then, don't we also have a Ka, because bicarbonate is amphoteric. So don't we also have Ka equilibria happening here? We do, but yeah, it's accounted for. The same thing with carbonic acid. But we don't have to do that. This is just a base solution. There's only carbonate in here. The base solution, we just look for hydroxide donors. One other equilibrium we would consider would be Kw, but these would be it. And so the bases, these are listed on the chart, and we can find these there. All right, the last part of chapter 16 deals with structure and acid and base properties. This is supposed to be covered in Chem 1A, so I'm not going to talk about it right now. We did talk about a few things in the past, but we have a lab dealing with acid strength later. We'll talk more about it then. So that's it for chapter 16. For the lab, let's do the remaining ion. What ion do we have left for lab?
Magnesium.
Okay. Magnesium. Okay, if your unknown has magnesium in it and we add HCl, nothing's going to happen. No reaction here. That is magnesium 2 plus and chloride don't react in the metathesis reaction. And then here, if we have this solution 1 and we add ammonium, we do expect to precipitate, but in this case, we shouldn't see any reaction. Magnesium ions should precipitate out with ammonia and water. To form magnesium hydroxide. Magnesium hydroxide is insoluble, so that would be the driving force for this, would be the precipitation of magnesium hydroxide. But again, that's prevented because of the Le Chatelier's effect. This is why we add the ammonium. So what we want to do is we want to increase the ammonium concentration to prevent this precipitation from occurring. Because if this precipitation occurs, then we're going to have trouble in the analysis of the aluminum, iron, and chromium. It'll screw it up. After this, we add the hydroxide. Is that correct? When we add the hydroxide, though, then there's no holding back this precipitation. So if we go solution 2 and then add the sodium hydroxide, we ought to get a precipitate, a white PPT. Is that what forms here?
Yeah.
And that white PPT is, now we have plenty of hydroxide to do that. We'll end up with magnesium hydroxide here. It's solid. Over here we didn't have enough. We were limiting the amount of hydroxide by buffering it with ammonium. Ammonium's an acid. Not a very strong acid, a pretty weak acid. All right, what did we do with the precipitate from 3? do we do with the precipitate?
Add ammonia.
Add ammonium? Ammonia?
Yeah, ammonia.
All right, so we go precipitate 3 plus ammonia. Did anything happen to the precipitate when we add ammonia to it? No. So basically NR. Well, that is, you know, if I have magnesium hydroxide, it doesn't form a complex or anything. Reaction. Okay, then what do we do with the precipitate?
Hydrochloric acid and the magnesium reagent, and we dissolve it and then form it.
Okay, we dissolve it, and so we take precipitate 4 and add hydrochloric acid, and the precipitate dissolves. All of it should dissolve. And that is the magnesium hydroxide plus 2H plus is going to go to magnesium 2 plus 2 water. This is a metathesis or acid base. Fits both categories. Just a double replacement type reaction. All right, then we do the magnesium reagent plus what?
Sodium hydroxide.
Plus sodium hydroxide. So we take solution 5 plus sodium hydroxide plus the magnesium reagent. What is the magnesium reagent? Anybody know what the magnesium reagent is?
Just magnesium reagent, that's all it reveals.
Okay, how about, does anybody know what it does?
It should turn the precipitate blue, it should form a blue lake.
Okay, basically magnesium reagent's a dye, and we have a white PPT, and we're going to color it using the magnesium reagent. And we don't need a whole lot of magnesium reagents, just a little bit, and the precipitate's going to be contaminated. That's why the double dagger here. The double dagger is to indicate that it's been contaminated. The magnesium reagent, a little bit gets incorporated into the crystal lattice, which yields a color. But it's not a blue solution. This is a blue solid. So in order to see this, I'll bring this up because some people ask me, is this the blue lake? And all I see is a blue liquid. That's not the blue lake. The blue lake is, you have to centrifuge it, and you get a gelatinous precipitate at the bottom. It's like a layer of Jell-O. So this is the precipitate above the liquid. And so the reason they call it a lake is because it looks like you made a little miniature lake in the bottom of your test tube here, with the liquid, the sky above it. And so you look for that. This particular test. Okay, are there any questions about this? Now, if you finish your unknown, you can repeat your unknown. You can repeat certain steps of your known. You know, we have reagents there, so you can do some test reactions if you want. If you're satisfied with how the unknown went, you go on to the anions. The anions, you got to watch out for the nitrate test because there you're going to use concentrated sulfuric. I don't know if we have it out, but concentrated sulfuric causes severe burns, like 3rd-degree burns on the skin. You have to watch out for this stuff. All right, any questions? That's all for today.